Okay, good evening everyone. Let us get started. So yeah, welcome back. We are restarting after quite a long time. So uh, before we stopped, we had a elaborate introduction on what all things we are going to discuss. So today we'll start with the first topic, that is, first we'll understand DC machine. So prior to that, I have already discussed about a brief understanding of torque production. What we need for torque production: we need two magnetic fields which are stationary with respect to each other, and we looked at different ways of realizing that, and we realized different machines. First, the simplest case, that is the synchronous machine, then induction machine. We looked at the rotor bar currents. We understood rotor bar currents, and first we understood flux linkages of rotor bar currents, then induced EMF, then bar current. Then from there, due to bar current, what will be the rotor magnetic field? We understood all those things, and after that, thereafter, we discussed about DC machine, and we had a brief discussion on what is going to be the next topics, like dynamic modeling. We are going to discuss about the dynamic model of a DC machine, and there the power electronic converters, what type of converter is required for driving a DC machine, and thereafter we'll discuss control of the DC machine: inner loop current control, outer loop speed control. Step by step we'll realize all those things, and it will conclude with the simulation using MATLAB simulation. So just like we discussed the field in AC machines, like we realized the rotating magnetic field, then flux linkages, and different things. Now we will look at the field in DC machine, which only we have mostly looked at the stator. What happens if stator is excited and both are excited, and we have not discussed how torque actually gets produced due to the interaction of two fields. So that is common for all cases. We will discuss that for DC machine, and therefore thereafter we will go on with the other cases. So let us get started. We are going to discuss on magnetic fields and in DC machines, and torque production in DC machines from magnetic field perspective. So just to give you a basic idea of how a DC motor look like, what all internal parts it has. So DC machine, we understood that we require some field, uh, that is the magnetic field due to the stator. We passed some DC current through it, and that produced a stationary magnetic field. So there is another option: we can replace the field winding by a permanent magnet on the stator, like as it is shown here. And Apple Pen. Oh, charge is there. That is the problem. Yeah, now it is good to go. So if we replace that field winding by, so either we can have a field winding as is shown here, like this is the pole, and you can see the copper winding wound around that. So that is the field winding, and we can realize the same by putting some permanent magnets on the stator. Now along with that, you will have some certain other parts, like a rotor. You will have conductor. This is basically the rotor. Whatever I am trying to indicate, that is the rotor. And you have different gray color boxes, deep gray color boxes, which are the commutator segments, or which are basically the T-turn slot of the rotor magnetic part or armature. And actually these are the this on one side You can see that on one side you do not have any other thing, only the coil windings are, the end connections of the coils are there, and they are getting connected on the left hand side. If you look at from this side, this is the commutator. You can look at the different commutator segments, and all the coils are basically getting connected there on the commutator segment. Probably we'll go ahead and look at uh, uh, winding, say lap winding or wave winding, whatever, any one case for armature winding of a DC machine, that will give us a understanding about how what is the role of the commutator and brush. So this is the brush. So probably from this side the brush gets inserted, and they touch the commutator segments and the commutator, yeah. So this is the construction of a DC machine. This is a permanent magnet DC machine where the field is realized by permanent magnets, and on the right side you have field winding on the stator. That is the because it is copper winding wound, so that is called wound field DC machine. So just a 2D cross-sectional view of a DC machine that will show the different parts, the electromagnetically relevant parts. Like this is deep ash color outside, that is the stator, that is a magnetic steel which has reasonably good magnetic characteristics. Then the blue color, light blue color one, that is the rotor, that is also made up of magnetic steel. So in the rotor slots you have red or ash color uh, rectangular boxes which represent the armature winding, and on the field you have again red and ash color boxes which represent the field winding. The rotor at the center, there is some white space kept. Actually that is the shaft. So shaft is generally not made up of magnetic material because shaft needs to transfer the mechanical energy. So the mechanical strength of that material has to be good. It need not be magnetically good, magnetically highly permeable material, but its magnetic strength or mechanical strength has to be very very high. So that is a different material for the shaft, which is generally at the center. So yeah, I have indicated all the different portions. Now we will understand the different names of the different parts. Like this is the stator pole, this is the stator pole. So stator pole, main part where winding is put, that is the stator pole body, and the part which gets expanded to cover more parts of the ear gap. So this is like the cross sectional area is more it is extended on both parts. So this portion is the pole shoe. So this portion is the pole shoe, stator pole shoe. Then on the rotor you have different teeth, that is the blue one. These are the teeth, and in between two teeth you have slot um, where the armature conductors are placed. Now the flux lines will be something like this. Say they are going downwards, so they will have to complete their path, and for that they will have to flow through the outer body, that is called as the yoke portion. Yoke uh, that 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 helps in the magnetic flux to close its path. So on both sides you have the stator yoke through which the flux lines uh, complete their path, like this. And in the rotor portion also they will enter from the tooth portions, and they will have to flow through the middle portion, that is called as the rotor yoke. So this middle portion after the slot and till the shaft, this portion is called as the rotor yoke. So we have understood the different parts of the stator and rotors which are magnetically relevant. Now we will jump into the first case. We understood how to realize what happens if only stator winding is excited. So to understand the effect of slotting and other slotting, etc., so first we will consider this case where only the field is there, like field winding is there, and in the rotor it's a smooth rotor. There are no slots on the rotor body. So that's a smooth, only a annular ring kind of a thing, annular cylinder, that is that is put as the rotor. And suppose for the simulation purpose we are having some field current of 1 ampere, number of turns per stator pole. What does that mean? So this is one stator pole. Sorry. So this is another stator pole. So on this, if this is the stator pole, on this we'll have different turns. Like this we'll have different turns. We may have different layers of turns. So on one pole, whatever is the number of turns, that is uh, that is denoted with indicated by ENF. ENF is the symbol used for that thing, that is number of turns per stator pole, that has been taken as 500. So the field MMF, what do you mean by MMF? MMF is magnetomotive force, that is analogous to EMF in electrical circuit. So field MMF per pole is nothing but number of turns into current, that is 500 ampere turns for this case. So this is the first case which we directions are indicated as current directions are indicated with this cross and dot directions. So dot means they are coming out. So dot means they are coming out out from the screen, and cross means they are going into the screen. So if that is the case, then because of this current, what will be the direction of the magnetic field? If I indicate the flux line direction, it will be upward, right? Dot and cross, if it is like this, it will be upward, and here also it will be upward. Now let us try to understand which stator pole is south pole and which stator pole is north pole. So if it is going upward, that means this is the stator pole surface. They are going into the stator pole, that is it has to be a south pole. On the other side, on the for the bottom stator pole, flux lines are coming out of the stator pole surface, which I am indicating with this red color. They are coming out from the surface. That is why this stator pole has to be north pole, and vice versa. It will be so the opposite pole will get induced in the rotor, because that is a ferromagnetic material. So 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 on the rotor, this is the surface. So flux lines are coming out from this surface, the rotor surface. That is why we have to have we will have north pole on the rotor top side, and south pole, because flux lines are going into the rotor surface. That is why we will have south pole on the rotor surface. So in this case we can see that we have south pole on top, north pole on bottom for the stator, and the opposite poles are induced right under that. So if north and south pole are there, then what do you expect? There will be a very high attraction force between them. So because we have south pole like this on the stator, and we have north pole induced on the rotor, so there will be a very strong force between stator and rotor. So if I consider the force on the rotor, for this case rotor will be attracted on the upward direction. Here everywhere it will be radially outward direction, there will be some force, and everywhere there will be some radially outward force. For this case also, like the rotor will get attracted in the downward direction, so it will be radially outward everywhere. So that is about the force that will electromagnetic force that will be there if only stator is excited. That we can understand from basic understanding of force between north pole and south pole. That is very obvious to understand. Now we will go it seems that there is no torque in this case, so there is no net movement of the rotor, because if we assume that if we consider the rotor net, say some force that is acting, say F R1, that is acting on the upward direction. If we take the component of all the forces along the y-axis and take component of forces along the x-axis, then we will see that uh, basically on the top side, whatever x-axis forces will be there, whatever will be on the right side, that will get cancelled by the left hand side forces, but there will be a net y-axis net force along the y-axis, positive y-axis. So let us say this is the force, and for the bottom side, similarly along the positive x-axis and negative x-axis, the forces will get cancelled uh, on both sides, and there will be a for downward force applied on the rotor. Now if we look at this case, because this is a symmetric case and FR1 and FR2 are equal, so there will be no net displacement of the rotor because of this magnetic force, but it will be no displacement. What does it uh, assume? It assumes that it is a rigid body. What is the meaning of rigid body? Rigid body means a body, no matter how much force you apply, how much pressure or force you apply on the body, or stress is the correct word to use for forces. So no matter how much stress you apply on the body, it will not deform. It will not, the shapes of the body will not get changed. So that is the meaning, that is what we mean by rigid body. So if we consider or assume the rotor as a rigid body, that is the magnetic forces do not deform the rotor, then um, then there will be no displacement and no effect of this radial force. But actually any body that is not no body is a rigid body, there will be some kind of compression or expansion because of the forces. So there will be some small micrometer level of uh, compression or expansion of the rotor due to these radial forces. So we'll understand that actually this radial forces, if they go on change, then there will be some um, compression expansion, and that will lead to some vibration of the motor. So vibration is due to these radial forces. We'll understand that. Now let us try to focus on field lines and magnetic field density plots only. So next plot, the right hand side plot, is the color plot, where the color indicates the flux density. So this is the B, flux density in Tesla. So the red color indicates the maximum flux density, and the blue color indicates zero flux density. So you can correlate between these two in this portion. If I probably erase a few parts that I have made, so you can see where all do we have blue. So you can see that on the rotor, this portion, you have very quite low density of flux lines. That is why you have blue region in the corresponding to that. So here in this portion, whatever is the density of flux lines, in this portion whatever is the density of flux lines, in this portion flux line density is quite high compared to that, right? That is why you see that here it is green. Green means medium flux density, whereas blue means lower flux density. So because this portion all the flux lines that come from here, here, so all the half the, so almost 90 degrees, so from this portion to the rotor stator pole, in this or in this angular distance, whatever flux lines are coming in from the stator, all of them will have to cross this horizontal portion that I tried to indicate with thick red line. So that is why you have high flux density in this region, both on the both sides. Whereas flux lines, some of the flux lines come in from here, and some flux lines come in from the central portion. That is why in the central portion flux densities are quite low, but as you tend to go on the along the x-axis, the flux densities become quite high. Now on the stator also you can see that on the stator flux lines come in, and then they get divided uh, to flow on the both sides. And that is why in this portion you have, because flux lines have already uh, got diverted into the side, both sides of the yokes. That is why in these portions you have quite low flux density. And the yoke, because it's almost the same flux line flowing from, so all the lines that I am trying to indicate, all of them are having the same flux lines, same number of flux lines flowing. That is why you have, throughout the portion you have a yellow region that indicates a uniform flux density. In this portion you can see flux density is quite high. And again in the middle portion, in this portion especially, you have reasonably high flux density, whereas on the sides of the pole shoe you have reasonably low flux density. So you can also understand that there is no need to make this pole shoe as wide as it is in these portions. So right under the pole body, whatever is the width of the pole shoe, it can actually reduce on the both sides, because this portion of the material that is not being used effectively. So if we shape it, if we generally, if you see the pole shoes of DC machines, they will not be of this shape, and they will be, so whatever is the width here, you will slowly reduce it. You slowly reduce and this will be probably a more realistic pole shoe for a DC machine, because this area whatever we are leaving, that is not utilized well. We are not, flux densities are quite low in those regions, so we can cut down on those material, on that much volume of the material, and that will lead to weight reduction and other weight reduction, material saving, etc. All those things will be there, because those portions are anyway not being utilized properly. So pole shoe, yeah, that will be a more realistic shape. So I will probably stop for a moment. Is there any question till now?
Sir, could you please quickly recap that field in the left side portion once?
Left hand side means?
Without ANSYS simulations.
No, no, both are ANSYS simulations. One is a color plot, another is a only the flux line
Oh,
distribution. So
flux
you
lines,
mean
sir.
this one, flux
Yes,
line?
sir. Yes, yes, yes. Till that creation of the poles in the rotor and stator is clear, sir. After
Okay.
that, you have said forces, right? Could you please quickly recap that once?
Okay, forces anyway I will discuss again. So if you have doubt on the for the forces, I'll discuss it again. So just to indicate, so this is the south pole and this is the north pole. So if you have south pole and north pole facing each other, so you will have some forces. What will be the direction of the forces? What will be the type of force? That will be attraction. So the rotor will be attracted radially outward and the stator will be attracted radially inward, right? So you will have force acting all over this place in the radial direction, and you will again the rotor will be attracted radially outward in these regions. So you have these radial forces. Now we will eventually see that uh, this does not have
Yes, sir.
any tangential component. So for torque production, what do we need? If we have a circular body, if it has to rotate, then we will need some couple, means some tangential forces. So if this is a point, if this is the diametrically opposite point, we need some couple like this. We need some tangential force like this, say ft and ft on the opposite direction. That will that will cause a couple in a certain direction. So this is a couple or torque that will cause the rotation of the body. But we will eventually see that if only the stator is excited for a DC machine, or that for that matter in any machine, if only one magnetic field is there, then there will be there will be only force in the radial direction between the stator and the rotor, and it will not lead to torque production. That you, if you have laboratory, if you excite the stator only of a DC machine, it does not rotate. You need to excite both the stator as well as rotors, right? So yeah, about more details that I have indicated, like the radial forces, rigid body, that I will eventually discuss once more. That is only to give a uh, indication what this force causes. So yeah, so let us take a let us have a magnified view of the flux lines in the pole regions. Say this is the dotted line which I am trying to expand and show you. So you can see that yeah, flux lines, they tend to, they come and then they tend to bend, then they tend to bend along the uh, along the this pole shoe region, and that causes flux density. You can see whatever is the flux density in this region, how much dense the flux lines are. But if you see in this region, flux lines are, the density is quite low. That is why I told that you may you are not utilizing this whole area effectively. So you could reduce the width of the pole shoe on the two sides. That will that will make the flux density uniform, and that is, there will be more utilization of the area. So yeah, as of now we will stick to the case that you have taken. Now we will look at the flux lines when they are passing through the air gap. You can see that all the lines, they are coming at certain angle. So this is the stator surface. They are coming at certain angle, and then they are leaving the stator pole and again entering the rotor pole, or the rotor surface, right? And in between you can see that the flux lines appear to be perpendicular to both the surfaces. So if I pick up this line, this looks like it is perpendicular to the stator surface as well as rotor surface. So if we have two concentric circles, say I'll expand some portion of that. So these are two concentric circles. If we have a line, which is perpendicular to both the surfaces, then that line actually is on a radius, and if this line is expanded, that will come and intersect the center of the circles. So in case we have two concentric circles, with the concentric circles means two circles with the same radius, with different with the same center with different radius. So if we have some line which is perpendicular to both the surfaces, both the circles, then the extension of the line will eventually intersect the center of those circles. So that means the line that is radial in nature, that is a radius, part of a radius. So that line indicates the radial, so the line actually is along the radial direction. So you can look at that in the air gap, all the flux lines, because they are perpendicular to both the surfaces, that is why we can understand that in the air gap flux lines are mostly radial in nature. It's all radial. And why is this so? Because if we look at one surface, say the stator surface, so we are looking at this portion, flux lines are coming at certain angle and they are leaving at certain angle. What determines this relation? So this is so for light we have Snell's law. Like if we have two medium with different mu, what is that mu called for light? uh, I forgot the name, or
Refractive index.
the term
Refractive
used
index.
for
No.
refractive index. That is correct.
Refractive index.
refractive in, that is correct, refractive index. So if some light beam comes here at certain angle, it will leave at certain other angle. So these angles, so the sine of these angles actually depend on, so sine theta 1 by sine theta 2, that is mu 1 by mu 2, right? So similar to that, for magnetic, so for magnetic boundary condition is also, there is a magnetic boundary condition similar to that. If flux lines are coming from a medium with certain magnetic permeability, say mu, and it is going into certain other magnetic permeability, say mu 2, then the angles, so if this is the radial line, so this angle is a theta 1, and this angle, whatever is this angle, that is, say we are taking angle with respect to vertical line, so that is a theta 2. I'll probably expand. So this is the vertical line, flux lines are coming like this, very near to the surface. So this is theta 1, and they are going something like this is theta 2. So sine theta 1 by sine theta 2 equal to mu 1 by mu 2. For this case, mu 1 has relative permeability of mu r, that is for iron, very high, and mu 2 has relative permeability of, so mu 1 is basically mu r into mu 0, and mu 2 is equal to only mu 0, because that is air. So this ratio will come out to be mu r, which is typically in thousands or few thousands to tens of thousands. So let us say 10,000. So if that is 10,000, then uh, so it is possible to show that this theta 2 will be, so sine theta 1 by sine theta 2 is a very high number, and this very high number means sine theta 2, this value is very small compared to sine theta 1. When is this value, when is the value of sine theta minimum? When theta 2 is 0. that means this theta 2 is 0, that means this line almost goes along the vertical line. So that is why, because of the very high permeability of the magnetic material and one relative permeability of the air, when we have interface of iron and air, so whatever angle, so it may come into the air iron interface at any angle, but it will always leave while going into the air almost at 90 degree or very close to 90 degree, 89.5 at certain, at some angle like that. So it will be that small, or it will be that close to being a vertical line. So always, probably we have seen some previous cases also, some boundary between air and iron in the initial lectures. All those cases, whenever we have boundary between a ferromagnetic material and air, flux lines will be always perpendicular with respect to at the interface. So at the iron and air interface on the stator side, it is perpendicular to the stator surface, and from the air gap and rotor surface interface, it is perpendicular to the rotor surface. And stator and rotor surface both are concentric circles. So if it is perpendicular to the stator surface and perpendicular to the rotor surface, then it has to be a radial line. So this tells you that because in electrical machines you have a very small air gap, and following this magnetic boundary condition, we will have the flux lines in the air gap as radial lines, very small radial lines with the length of air gap, the air gap, that is G. So that is about that. This tells you about the flux lines in the air gap, and that is actually going to be important. Now let us try, let us go on along the air gap. Let us take a red circle, as I have indicated, that is at the air gap. That is a contour along which B is plotted. The flux density is plotted, and the flux density direction is also plotted. So whatever, so say we are at this point, and the B vector has certain magnitude and some direction, say like this. So what we will do is we will this is the B vector at this circumferential position on the air gap circle. So we will take the components of this B vector along the tangential direction and along the radial direction. That is what we will do. So this is a simple thing to do. Suppose at any point, so this is the air gap circle, this is the center, say. So this makes some angle, say phi, at the center, this point, with respect to horizontal line. So at this point, if we know the direction of B, say direction of B is like this. This is B vector. Now this B vector will have to be uh, we will have to take the components of this B vector along this first line, which is a radius, a radial line. So this is the radial direction, and on this line, if we draw a tangent, then that is the tangential direction. So we know, so we will get the magnitude and direction of B vector at all points of this red circle. I have only indicated one point. Similarly, we will have different points on this red circle, and once we get B and its direction, we will take the components, like if this is B, and we can get this angle, say theta whatever. So we can calculate this radial component as B into cos theta, and this tangential component as b into sine theta. So that we can do for all these points which where phi goes on changing. So first we'll have some phi very close to 0, then we'll have another point. So like this we will move on this air gap circle and we will plot these two quantities, b radial and b tangential. So let us go the do that. And what about direction? So if b radial is in the radially opposite direction or radially outward direction, then we will assign positive sign towards it, positive sign to it. That means if B is in the radially outward direction, then for this location, then we will have positive B rad for this. On the other case, for the flux lines, like this is south pole, this is north pole. For this case, I am discussing the flux density. You can understand the direction will be outward. So that is why at this location, like theta equal to 90 degree, we expect B radial sign to be positive. On the other case, here on the other case, in the at this point, because this is north pole, flux lines will be going out, going in. So B vector direction will be radially inward. So we expect that at theta equal to 270 degree, that is here, we expect the B radial sign to be negative. And what about the tangential component sign? If because we are moving in the anti-clockwise direction, if tangential component of B direction, the direction of tangential component of B is along the anti-clockwise direction, it will be considered as positive. If it is opposite, it will be considered as negative. That is about the convention. Now if we actually plot it, if we 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 uh, do this exercise, we take different points on the air gap circle, take the b magnitude and direction, and resolute it into two components, this radial component and tangential component. Here I am only showing the radial component. You can see that under this pole, under this top pole, you have a reasonably high positive value of B radial, right? And in the interpolar region, like these regions, you have hardly any flux lines. That is why you have zero. You have nearly zero flux density in this region. Similarly, in these regions, and again under the opposite pole, that is under the north pole, because flux lines are going in the inward direction, that is why you have negative flux density, negative value of B rat in this case. So that is about the distribute or the radial component of B if it is plotted along a air gap circle. Now let us try, this is understood I think, because south pole and north pole is well understood. South pole and north pole indicates the direction of the B also, and we understood no matter what, in the air gap, flux lines are mostly radial lines. So they are almost, and the density, you can see density in the air gap, flux lines are almost equal, the distribution is uniform. So in the iron portion, you can see that this portion has more flux density, this portion has less flux density. But if you look at the air gap, in the basically in the air gap, then you can look at that, say this line and this line, whatever is the distance, so whatever is the arc length between these two lines, the same distance can be seen for all the lines. That means the B distribution is almost uniform at the ear gap. That you can, okay, here B distribution color code in the ear gap is not shown, but anyway you can understand that that is almost uniform under a pole. So, and in the interpolar region it is close to 0. Now let us look at the tangential component of B. So this is the tangential component of B. So if I, so tangential component can be seen that under the pole it is 0, again under the another pole it is 0. Whatever this uh, thickness or very small value it is showing, that is only due to, while doing simulation we will resolve the geometry into very small portions. That is due to those uh, so, how what is the resolution of the small portions that we have, or as famously called as meshes. What is the resolution of the mesh that we take? That is because of that, if we take the resolution reasonably good, then we can say that it is 0 under the pole. But tangential component has some spikes on the edges, like this is one edge where stator pole has an edge, again stator pole has an edge here, stator pole has an edge here, and again stator pole has an edge here. So we can see that tangential component is high only at the edges. If either, in this case only stator structure is having some edges, so stator only at those locations we have some reasonable value of tangential component of B. And what about the direction? What about the signs? Basically, if I try to indicate flux lines, so a flux line, it is coming like this, or probably let's look at some other color. So say flux line is coming like this, it has to enter the pole, it will go somewhat like this, right? It will go somewhat like this. That means uh, if I draw this portion, this is the stator pole, this is the rotor surface. Suppose the flux line is entering here, right? So it is coming from here, it is entering there, like this. Now if you look at the ear gap, or at the middle of this air gap circle that is plotted in between the stator and rotor surfaces, you can see that the flux line direction has some component in the radial direction as well as in the tangential direction, and in this case it is in this direction, that is circumferentially anti-clockwise direction. So that is why at this edge, that is the first one, if this is 0 degree, this is some small angle, here there is a spike, there is a positive spike. So here, because flux lines are going like this, they will go like they will have some path like this, as I indicated. So for this case, along with some radial component, the flux line, or the B will have some direction in the clockwise direction circumferentially. That is why you have at this circumferential position, that is this portion, you have some negative edge. Again you have some negative edge here, because here flux lines are going like this, the direction is opposite. So that is why you have some direction in the circumferentially clockwise direction, and here flux lines are coming out from the rotor and coming out from the stator and entering rotor. So here it has some direction in the uh, anti-clockwise direction. So that is why you at this point or here you have some tangential component, uh, positive tangential component. Right, so we have understood the radial and tangential component of B due to uh, or for the case when only stator is excited. Now, what is the importance of this? Why do we require to do this? So, Maxwell's stress tensor, there is something called as Maxwell's stress tensor that is well discussed in electromagnetics books. So, that gives expressions of radial force density. What is force density? That is same as force per, so force per area, that is force density, similar to pressure, similar to stress, that is radial force density. So force, because it's a vector, it has, it can it has direction. So if we look at the force in the radial direction and its force density, then that is indicated with f, small f rad, that is radial component of flux force density. And conversely we can have tangential force density, f tang. So these are given by, for a given location, for a given point, say for any given point at the air gap, in the iron, it does not matter. If we have a point, and on this point we obviously for defining radial and tangential, where it is inherently understood that this point has to be with respect to some surfaces, so that we can define the radial and tangential directions. So at any point, if we know the radial component of flux density and tangential component of flux density, then the radial component of force density is given by the top expression, which is 1 by 2 into mu naught, which is the relative or the permeability of the free space, into radial component of force density square minus tangential component of force density square. Right, so if you just look at the radial component of flux density, tangential component of flux density peak values, say here peak value is about zero point 0.5 Tesla. Tangential component, although it's a very impulse kind of a thing, still the peak value is say 0.07 Tesla. So the radial component of flux density, it is 0.5 Tesla, B radial peak, and B tangential, that is about 0.07 Tesla. So there is about an order of difference between the tangential component and radial component of flux density. So if you do B rad square minus B tan square, that is 0.5 square minus 0.07 square, if you do this math, or if you simply calculate it, whatever will be the result, that will be approximately equal to zero point 0.5 square only, because this second portion is 1/10 almost, or almost a order smaller than the first one. If we apart from this, if you square it, then its impact will be quite low. So this can be approximated as only the radial component of flux density square for all practical purposes. So the radial force density is given by 1 by 2 into mu naught into B rad square. But for getting the tangential force density, the expression says that it is 1 by mu naught B rad into B tang. So this is multiplication of 2. So just to give you an idea, if we have two numbers, say m and n, if we have m plus n or m minus n, then we can apply these cases, say m very greater than n, then we can simply write them as m, and in this case also n. So this is about addition or subtraction. Similarly for addition
Sir, in both
addition of
cases, m,
squares.
sir. Sir,
What?
sorry. M minus
Yeah.
n is also m, right?
Yes. Sorry. Yes. Yes. You're correct. So if this is for the squared case also, then also it is if this condition can be used to simplify it. But on the other way, if we have m multiplied by n, then we cannot do anything. We have to do the math and get that right. We cannot use anything like this if it is multiplication or division, or especially multiplication. Division also we can indicate as very high or very low, but multiplication we have to do that and get the value. So for tangential force density, we have a very high value, say b rad multiplied by b tang. That is what the expression tells. Now let us try to look at the radial component of force density and tangential component of force density. That is what I was trying to indicate earlier. So radial component of force density, what is that? That is simply b rad square. So for this portion, you have b rad as positive. For this portion, you have b rad as negative. But be positive or negative, no matter, irrespective of that, if you take the square, it will always become positive. And what is the meaning of positive? Positive means it is radially outward. So if rad, if it indicates the force acting on the rotor, then you have the force acting on rotor like this. So the radial component of force density, it is about a constant number under the pole, and here it is always radially outward, here also radially outward, right? That is about the force acting on the rotor. And using Newton's third law, the same force will be acting on the stator also. So stator will be experiencing force in the inward direction, because the rotor will be attracting the stator in the inward direction, right? That is about the Newton's third law. So radial component of force density plot, if it is plotted, then on the both sides, on the top it will be radially outward for the rotor, for the bottom it will be radially outward for the rotor. So it's like some net radial force is acting on the upward direction, and some net radial force is acting on the downward direction. But that will not lead to that will if it is a rigid body means it does not deform. So if we have a cylindrical body like this, and if we apply some force on this, rigid bodies will not deform. But if we okay if we apply some force on a elastic body, then due to application of force it may have some small deformation, it may have some small, very small micrometer level deformation, depending on obviously the Young's modulus and other the amount of force applied, all those cases. But elastic bodies will tend to deform. So assuming the rotor to be rigid body, the rotor does not deform, and there is no force, no net force that leads to displacement of the rotor, because both these forces tend to cancel each other, one upward, another downward. So no net force along vertical direction, no net force along horizontal direction, so the rotor does not move in either direction. So if we so radial force does not lead to um, any displacement of the rotors. Now let us try to look at the tangential force density plot. If that is done, so what does that tell you? So tangential force, tangential flux density is 0 under the pole. So no matter what is the radial component of flux density, tangential force there under the pole will have to be 0. That is why tangential force under the pole, that is this portion under the upper pole and under the bottom pole, that is 0. But there is some there are some tangential force densities on the edges. Now let us try to see. On this edge, that is this edge, we have some positive BRAD, positive radial component of flux density, and on the same edge we have some positive tangential component of flux density. So in the first edge we expect some positive edge or positive impulse kind of a thing in the tangential force density. Now for the next portion, this edge, that is this edge, we have again some radial component of flux density, that is positive, but here it is negative. So next one we expect that tangential force density will be negative. Third edge, that is this edge, we have BRAD negative and B tang also negative. So again at this edge we expect some positive tangential force, and on the fourth edge we have radial flux density as some negative value, and here also tangential for flux density is some positive value. So at this edge we expect some negative value. So what do we expect? Positive, negative, positive, negative. That is what we expect. Let us see that. Positive, negative, positive, negative. So we have some force acting in this small area. So some small tangential force density applied in this small area, that is in this direction, positive. Some small tangential force or some tangential force is applied in this small area, that is negative, that is in the clockwise direction. Again a small tangential force or some tangential force is applied in this small area in the positive direction, that is anti-clockwise. And again some small tangential force density or some tangential force density applied in this small area, that is again negative, that is in the clockwise direction. Now if we try to calculate the couple because of all these forces, let us assume that it is some force, some area, say A, which is almost the same. This is small area wherever you have some tangential force density, small area, or you can see that is symmetric. So whatever value we can take the same area value for all of them. So we have some force, anti-clockwise direction force here, clockwise direction force here, both are of the same magnitude. Again some anti-clockwise force here and clockwise force here of the same magnitude. So you can see that this force and this force, they make up one couple that make the rotor to rotate in the clockwise direction, and on the other side you have this much force and this much force acting on the rotor. They tend to make the rotor rotate in the anti-clockwise direction, but both these couples are equal, so they tend to cancel each other. So for this case there is no net torque acting on the rotor. That means that
तेरे को वीडियो क्या
there
भेजा
is
था
no
पहले?
net torque production
एक भेजा
if
था ना
only
तेरे को
field winding is
वीडियो
excited.
इंस्टाग्राम पे.
I think someone's audio is not
हाँ,
muted.
थ्रेड्स आजकल थ्रेड्स बनने लगे हैं उस पे ना.
Yeah, please mute yourselves. So probably we'll stop here. Next day we will start with the case So we'll understand first. We have understood the simplest case.
Mhm.
What happens if we consider a slotless armature? Now we will put some slots on the armature and understand what is the impact of slots on the radial or on these flux density distributions and tangential component distributions, and we will stick to the first case only, that is no excitation in the rotors, only stator winding is excited. We will look at this case and we expect the same thing, same output, that in this case also there will be no net torque production because of uh, because of this excitation. Yeah, so we will continue on the next day. Any question till this point?
So maybe probably in the next class, can you explain 5 minutes about the Maxwell uh, that tens stress tensor?
uh, what to explain actually, because that is a derivation, that is a elaborate mathematical derivation, and the final expression is this. So only the final expression is of help, usefulness to us. So that is a mathematical derivation, nothing else. You can look at books like um, what is the name of that book, electromagnetics, elements of electromagnetism, or okay, I'll tell the name of the book in the group. That is some elaborate mathematical derivation, nothing else. So I do not intend to discuss any derivation that much involving math here, because we only need this final expression, nothing else.
Sir, the 1 by mu naught value, I'm getting around 8 lakhs. Can you comment on this value, 1 by mu naught and 1 by, because it is 4 pi into 10 to the power minus 7.
Yes,
It's
that
giving
is
me a very big
mu naught is,
value.
what is the mu naught value? 4 pi into 10 to the power minus 7, right? Henry per meter, if I'm not mistaken. That is the value,
1
yes.
by that,
That is the value.
1 by that one will give some kind of lakhs.
Yes, that is correct. Some lakhs.
But in the graph, you have shown only 0.1 because the mm
That
squared you
is
have taken.
mm square. So that will give in Newton per meter square. If you uh, change the unit to Newton per mm square, then you will get these values. What are the values here? It is say some point 0.07. This is, earlier one was 0.5. This is some 1 by 4 pi into 10 to the power minus 7. This will give, the unit will be Newton per meter square. Now meter square to millimeter square, you have to multiply it by 10 to the power 6. So if you multiply this whole thing by 10 to the power 6, then this one will become Newton per millimeter square. So only you will have 40 pi. So you'll have some 40 pi. All those things will go away. This number you will have. Yeah. If you look at the value, it will be approximately like that. 0.02. Okay. Any other question? If not, let us close today.